So welcome back. Now, in this module, this video, we'll be talking about design of Flocculator, which is the second unit operation in the coagulation setup. So what you see in this picture is a tank. You can see here, this is the tank, narrow tank, is a long, narrow tank. And what you are seeing is a central pipe. This is a shaft where you are seeing three different setups are now attached to the central pipe. So this is each of these we calling as a flocculator setup. So what is having you can see here narrow blades are there. Narrow blades are there. So this is the width of the blade and this is the length of the blade. So this is the area of one blade. So three blades are there one side and four sides. So 4 into 3, 12 blades and one single setup of the flocculator. So there are three setups, 3 into 12, 36 each of the area of the blades, right? So the total power required for rotating this entire shaft should be distributed among the three setups. So equal to P by 3. So when you are calculating the area of the paddles, so we have to calculate the power contribution towards the each of the setups. If two are there, total power divided by 2. If three are there, total power divided by 3. Only single shaft like this, you can see here. The total power is distributed in the among the entire blades of the flocklet, right? So now this is horizontal axis, so moving, and this is a vertical axis. So the rotational speed, everything will be varying compared to flash mixer. Relatively lesser, relatively lesser rotational speeds are operated in the flocklet. So now regarding the design parameters, if you look at the design parameters, you see uh, mainly the the main parameter is G, the mean velocity gradient, and the definitions are same. The power requirement P is equal to G square V mu. The same formulas we are used there. V is the volume of the tank. Volume of the tank you are going to calculate by multiplying the detention time. Here we are using 10 to 40 minutes of detention time. And the mean velocity gradient is around 10 to 75 per second. So compared to the higher velocities, higher values of flash mixer, where we are gone more than 300 per second. And what we are then again the relative velocity also the same thing. Relative velocity is equal to VR the VP minus VW. So VP is the velocity at the tip of the blade and VW is the velocity of the water across the blade. So what we are having is the relative velocity, which is equals to 75% of 75% of the velocity at the tip of the blades. The values are also given here. VP is equal to 0.2 to 0.8 meters per second, and VW is the velocity of water at the center tip of the paddles. And again, power input to the impeller is the same thing you have calculated based on the coefficient of drag. You are having P is equal to half of CD, CD into A rho VRQ, where VR is the delta velocity. And depth of the tank is 3 to 4.5 meters. And then we have a power check, 10 to 36 watt per MLD of flow. Besides this, we are having two more checks are there. And one is a dimensionless value GT, 10 to the power 4 to 10 to the power 5. Here G is per second and T is in second. So again, we are having one more based on the different type of coagulant concentration, detention time, and G value. the numerical value g to the power of 2.8 T into C, it will be equal to 44 into 10 to the power of 5, where G is the optimum value, C is the concentration of coagulant in milligram per liter, T is detention time in minute. By using these also, we can assume the G value and then start doing the iteration process. The rotational speed of the paddles, you can see here, it is less than 20 RPM, whereas in flash mixer, we are going up to 140 RPM. Let us quickly look at a small problem. Design a flocculator chamber for water flow 300 meter cube per hour, which is equals to 7.2 mld at a 20 centigrade. Sizing of the tank is the first step. To go for sizing, we need to calculate the volume of the tank. To calculate the volume, we should go for the detention time. 10 to 40 minutes, I am taking 20 minutes I am taking here. So detention time multiplied by volumetric flow rate or discharge is going to give you the volume of the tank, 100 meter cube. Then you have to go for a rectangular tank you'll take, assuming L by B is equal to 2, L by B is equal to 2, and H by B is a 0.4, 50% of that. The width is less and depth is more. The height, depth is less and width is more, we're assuming here. So substituting here, ultimately I'm going to get the dimensions. L into B into H, substituting here. B is equal to 5 meters, L is equal to 10 meters, and H is equal to 2 meters. That means we are having a tank like this. So this is your L, this is your B, and this is your H, right? So now what you are going to see is the second one, computation of power requirement. We calculate the volume. Based on the volume, we should go for computation of power requirements. P is equal to G square V mu, the standard formula. So mu is the absolute viscosity. Temperature is given 20 centigrade. Based on that, mu is equal to 1 into 10 to the power of minus 3 Newton second per meter square. So now 40 per second, up to 75 seconds we can go per second, 75 per second we can go here. So we go for 40 per second. Using that information, I calculated as 161.4 or 162 watts. So power requirement, now you're going for a check per unit flow of water. Power requirement is 161.4 watts divided by 7.2 mld is giving you 22.36 watt per mld. So, but the check value is at between 10 to 36. So 22.36 is within this range. So no problem. We can have the G value as 40 per second. Second check also I can go for verification. G into T should be between the range of 10 to the power of 4 to 10 to the power of 5. G is 40 per second and T is 20 minutes. Minutes are converting into seconds. So it comes out to be 48,000 is equal to 4.8 in 10 to the power of 4. So between 10 to the power of 4 to 10 to the power of 5. So this check is also satisfied. So that means we are now cross-checking whatever the value of G assumed within the permissible range or not. Now let us go for the dimensions of the tank. So here we have to go with some small assumptions. What are the assumptions we had? Already sizing you have calculated. L is equal to 10 meters, B is equal to 5 meters, H is equal to 2 meters. So I'm drawing this. So this is my B and this is my L. This is my L and this is my H. So B is equal to 5 meters. So this is 5 meters. So now what we are doing is, you remember, you should give some spacing on both sides of the blades with respect to walls and blades with respect to floor. So what I'm assuming is, I'm assuming one single paddle system here, okay, and then assuming 0.25 meters spacing, I'm leaving from the top. From the top, I'm leaving, and from the bottom also, I'm leaving here like this. Total height is 2 meters. 2 minus 0.25, 0.25, remaining is only 5 meters. 5 meters is the height of the entire paddle here. So what is the radius here? Radius is half the height. So 1.5 divided by 2, 0.75. So this is the radius, okay? Or usually the radius should be taken up to center of this. But because the sizing of the paddles, the sizing of the blades rather, the blades here we call, the blades is very, very small. So even we take the edge to edge, it will not make much of a difference. But theoretically, we should go for the center to center of the blades. In this problem, I am taking edge to edge so that our calculation will become much easier, right? So in this case, now zero point 0.5 meters is, 0.25, zero point 0.5 will go over. Now, what about this, the other dimension here? You can see this is 0.5 meters is left on either length of the tank, and both sides we are leaving a 0.25, 0.5, 0.5. So length of the tank is 10 meters, leaving 0.5 meters this side and 0.5 meters that side. Effective length of the shaft is 9 meters. So the length of the shaft is 9 meters, okay, 9 meters, and width of the blade is a B, okay. So now area of the blades is length of the shaft, width of the blades, multiplied with number of blades on each shaft. 4 blades I'm keeping here. So what will happen? Length of the shaft is 9 meters. Width of the blade is B. Number of blades are 4. So it is equal to 36B in terms of meter square. So next step is we are going for a calculation on how you are going to calculate the area of the paddles. So area of the paddles you have calculated. Now we have to assume the rotational velocity. Rotational velocity it should be less than 20 rpm. I'm assuming a 6 rpm here. So Vp velocity at the tip of the blades here 2 pi rn by 60. N is equal to here what you are taking as 6 rpm. And what the radius here? Radius is half of 1.5, 0.75. 2 pi into 0.75 into 6 by 60 is equal to 0.47 meters per second. It should be less than zero point 0.8 meters per second as per the guidelines. That is all satisfied. The relative velocity is 75% of this, which is equal to 0.35 meters per second. That also we have calculated now. So now the power requirement is say 0.5 into CD into A into rho VR cube. So now what I am assuming is how many sets of paddles we are going to keep. That is the most important thing here. Okay. So now what you see in this picture, this depth is 1.5 meters. The depth of the tank is 1.5 meters. So this depth of the tank is 1.5 meters. So automatically this side also will be equals to 1.5 meters. The total width of the tank is 5 meters. So if you simply keep only one per single shaft, lot of space is getting wasted. So for that, I'm trying to keep two single shafts here. So this is 1.5, this is 1.5. So total is 3 meters effective span, but overall span is 5 meters. So how 2 meters is left now? Out of these 2 meters, what I'm doing is 1.5 meters I can keep in the middle, and zero point 0.5 meters, half of 0.25, 0.25 I can keep it in the edges. Or I can keep 1 meter in the middle, zero point 0.5, zero point 0.5 and other than the edges also. So I'm having the two sets of paddles now. So what is the important thing here? The total power is now should be divided between these two sets of paddles. The total power is 161 watts. So divided by 2 is equals to 81 watts. So this is what I am using here. So 81 watts is equals to, using this equation, half CD. CD again 1.8 you are taking as a constant value from the manufacturer data, standard value. You can assume that A is the area on the blades, rho is nothing but the density, and VR we calculate as 0.35. So which is equals to 2.1 meter square. So 2.1 meter square is equal to 36B, because this is how you have calculated 36B. How 36B here? 9 meters length, 4 blades, and each width is B. 9 into 4 into B, 36B. So using that, I can calculate the width of the blade is equal to 6 centimeters. 6 centimeters is slightly more than 2 inches. That is sufficient. The blade size for each shaft is 9 meters length, 6 centimeters width, right? That's enough for only one blade. If you are to having two blades also, you can do similar calculations. So instead of using two sets of paddles, if I keeping only one set of paddle, what will happen? Just I'm rechecking the calculation. Because only one set of paddle is under operation, the total power should not be divided here. Single set of paddle, single value of power used to rotate it. So total 36B meter square is there, but total power is used 161 watts. Using that, I am calculating the width of the paddle is equals to 12 centimeters. So if you're going for two sets of paddles, is equal to 6 centimeters. Now one set of paddle, 12 centimeters. So this is how we are going to calculate the sizing of flocculator. The fundamental thing is how many sets of flocculators are using on a single shaft. Right? If two sets are used, total power is divided equally. If three sets are used, total power should be divided among these three. So this is how you are going to calculate the sizing of a flocculator chamber. In the next video, we'll be going for, next video we'll be discussing about design of a sedimentation tank.